Hello everyone, it's a pleasure to be here and to give this keynote today in course of the Automated Software Testing Conference. My name is Michael Felderer and today I give a keynote on going online reflections on testing machine learning based systems. I'm a professor at the University of Innsbruck in Austria and working on this interplay between software quality and AI. The talk is organized as follows. So we will first start with a motivation, giving an overview what the topic is all about and why it is essential today to reflect about quality assurance of AI-based systems, especially in an online context. Then we will discuss similarities and differences between online and offline testing, and then I will present you some current work that I'm doing on assuring collaborative AI systems, and finally I will pose challenges where I think the community should work on. Let's first go into the motivation. So quality and risk of ML-based systems are essential. There are more and more cases, for instance the self-driving vehicle issue that hit a bicyclist. This shows that on the one hand, machine learning based AI is very powerful today, but it also needs to be quality assured to mitigate potential risks. This doesn't only hold for autonomous driving, which is by far the most prominent context where most examples exist and are around, but for instance also in industrial robots that are becoming more and more intelligent, targeting Industry 5.0, where humans and robots work in a collaborative space and where quality assurance and risk assessment are also essential to keep safety issues low. That software engineering in general and software testing in particular play an important role in the context of engineering AI systems is very illustrative by this metaphor that has already been shown by Scully in 2012. Scully, working at Google, shows the hidden technical depth of machine learning systems, and there you can see that this black box, which is the actual machine learning code, or let's say the algorithms, is very small compared to all the engineering around the configuration, the data collection, feature extraction, the data verification, the serving infrastructure, monitoring, and so on. That's very essential, and AI systems, ML-based AI systems are always systems, where you cannot see the ML component in isolation whenever it comes to industrial application of such systems. And this is the context that we are talking about. So why are such systems different? What makes them different? So first we have the classical triangle of software engineering, considering time, then the resources to implement the system, the functionality that you want to implement or have to implement, and then the quality aspect. And these four dimensions contradict each other to some extent. I mean, if you want to increase quality, you either increase time, resources, or decrease functionality. So there is a trade-off between these dimensions. And modern ML-based systems even refine these aspects. There are a few new elements that come into play here. Namely, functionality is not as clearly specified anymore as it was in the past. Right? Functionality has now to deal with uncertainty that actually drives the functionality that is inherent in the learning of the algorithms. And even beyond that, we have to deal with self-adaptiveness. This means that the behavior might change over time. The system might be self-adaptive, learning from new data and refinement of algorithms. That's the one thing. And when it comes to the aspects of quality, then new quality properties play a role, right? On the one hand, data quality, which is for sure also important for traditional systems when you think about the data in an SQL database, but data quality becomes a first-class citizen because the behavior of these modern ML-based systems is driven by data, and therefore high quality is essential. And the second aspect is that also new quality properties are on the horizon and have to be considered. A very, very prominent examples here are typically explainability, that these machine learning based AI systems have to be explainable, or another aspect is accountability, and there are several properties which can be summed up under the term trustworthiness. Trustworthiness of AI, trustworthiness, which is also a topic of this year's ASD conference. There are several definitions of trustworthiness. In general, trustworthiness of AI contains both the usability aspect somehow, so targeted towards the user must trust the AI, but also the product quality aspects of AI. And you see that trustworthiness is a hot current topic. There are approaches to make this illustrative both from view. There are ethics guidelines, and there we come up with concrete dimensions that try to define what trustworthiness is about. So there we can see the accountability as a property. We can see also human agency and oversight, technical robustness and safety, privacy and data governance, transparency, which is linked to explainability, diversity, non-discrimination and fairness, as well as societal and environmental well-being. Then well-known consulting organization Deloitte has also defined trustworthiness, which somehow overlaps with the European definition, but is a little bit more pregnant. Therefore, I have considered it here. It considers fair, impartial, robust, reliable, privacy, safe, secure, responsible, accountability, and transparent and explainable. And these properties together form trustworthiness. So when you fulfill them, then the user might trust, because users normally reduce trust when it comes to such AI-based systems. For sure, there are also, like for classical quality properties, trade-offs. So for instance, when you want to increase fairness, then robustness might suffer, or some other properties might be harmed, like safety, for instance. Okay, so this is the general setting. We have systems, we have new quality properties, we have uncertainty, and in this complex context, we have to do quality assurance, and therefore there are for sure impacts on quality assurance, in particular that online testing is becoming essential. But first, let's go a step back and let's define what quality assurance means. Is it different? Is it largely different from classical quality assurance? So the first step is we need to define what machine learning engineering cycle is. And here I take the definition from a book that I really enjoy, from Andrei Burkov, Machine Learning Engineering, and he defines the process, which is not as curious, I would say. It starts with goal definition, then data collection preparation, then it has some feature engineering, the process where characteristics are extracted from raw data, maybe some image features or others. Then we have the classical model training, based on the labeled data, where your machine learning algorithm actually learns, yeah, and then we evaluate the model with classical metrics like precision recall, for instance, and then after this offline phase, the online phase starts when the model is actually deployed, may it be in the cloud, for instance. Then the model serves, it serves in a batch mode sometimes. This means, for instance, when weekly recommendations of all new songs for all users of a music stream are generated, or it serves human demands when they request it, for instance, when a credit card assessment is done, or they serve other systems, when they are integrated in autonomous driving, and in addition, for sure, models continuously have to be maintained, for instance, due to the concept drift, where new data with different labeling might request you to refine your algorithm to be still proper. Again, this what I showed is more or less the process of making or of developing a machine learning algorithm in context of a system. It showed mainly the approaches that are needed for the algorithm itself. It's again integrated in a system, and large parts of the system is traditional software, right? And here we can see from a recent survey paper that machine learning systems contain several parts. They contain for sure the data. Then they contain the learning program, which is more or less the code for running to train the model. Then for sure the model itself, and then also frameworks like scikit-learn, TensorFlow, and that's classical software as well. And then there are also different types of issues. We do not only have model issues, which are the classical machine learning issues, like overfitting, that people might know, or non-optimal regularization, things like this. There are also other issues like data issues, deprecated features, bundled features, incorrect data, noisy labels, and so on. And finally, there are also implementation issues like pipeline jungles, incorrect use of APIs, dead or experimental codes, buggy third-party libraries, platform-specific behavior, and so on. That testing is still important in this context is also shown by empirical studies. So recently a student of mine did, for instance, one. She did a exploratory study with startups in the AI area. So 10 startups were involved, and they were asked about their habits and needs with respect to software quality assurance in the context of AI. And as you can see in this figure, all of them stated that testing is essential to them. So this gives us good motivation to investigate further what testing in the context of ML-based systems, which I, by the way, abbreviate by MLS, is all about. So there is another very informative survey paper by Riccio et al. And it also defines what types of testing are there and what they mean, and investigates how many approaches in the different categories are around. And actually they distinguish 4 types of testing levels. So the first level is so-called input testing. Input testing is about analyzing the training data used to train the ML components, as well as the input data used at prediction time. So you could say also somehow this is the data testing part. Then the next part is model testing. Model testing is the classical evaluation of the ML model, that also AI machine learning experts have in mind, measuring, for instance, accuracy and this relates, when we transfer it to the software testing community, to unit testing, because you test this unit, this model, on this in isolation. Above the model testing layer, the authors distinguish integration testing. Integration testing is testing in which software components, including the ML models and hardware components or everything together, are combined and testing to evaluate the interaction between them. So a classical integration testing scenario that you need to evaluate intermediate steps. And finally, when the entire system is ready, then you do system testing. That's testing conducted on a complete integrated ML model system to evaluate the system's compliance with its specified requirements. And such requirements could be requirements to trustworthiness properties, like safety-related properties, as we will see later. Okay, and what we can see here from these statistics, so the authors found overall 70 papers, and 45, so most of them are actually about testing the ML model, so about this unit testing. Other areas, like input testing, integration testing, are more or less not considered here, and system testing do a reasonable amount, but we will see there is space for doing much more and coming up here with new test automation approaches. So if we dig a bit deeper into this study, which I find a very interesting one, then we also see that 55 out of the 70 papers actually investigates the generation of test artifacts. Which test artifacts are generated? So mostly it's about test input generation. This is the classical type of ML testing paper, to generate inputs, adversarial ones and so on, for testing the ML models. But also other aspects are considered. So the generation of oracles, for instance, this is mainly metamorphic relationships. We will also see that a bit later, and then also prioritized tests, mutation operators, and training data are among the generated test artifacts. Furthermore, what test input generation approaches are actually applied? We heard on the slide before that test input generation is the most prominent approach here, and approaches that are applied here are input mutation to a large amount and search-based approaches. These are the dominant ones. Input mutations are, for instance, affine transformations or change of pixel values, cropping if we are talking about images. Otherwise it's adding rain or fog if we think about autonomous driving and things like this. And in search-based generation of test inputs, it's about for instance generating inputs in autonomous driving. So for instance, to minimize distances in order to actually drive the generation towards violations of safety properties. Okay, and to go a bit further here, to give you this broad overview, what are the adopted oracle types in ML systems? So the mostly adopted ones, according to these papers, are metamorphic relationships, that help you to actually define the expected output via relationships. This will also play a very important part in online testing that we will then C. Then in addition, very plain ones are also used, domain-specific failures, a very weak form of oracle, but also differential oracles, where we have multiple implementations of the same algorithm that are compared against each other, used. Killing mutants is used, or misclassification of manually labeled inputs are used, but the most prominent ones are metamorphic and domain-specific failures. And the last aspect, then I continue and go beyond this very recent literature survey, is what systems are actually used in the context of testing ML systems. And there I just want to highlight that really the most prominent domain is advanced driver assistance systems. It has several reasons. I mean, this is a very prominent topic in industry. There are many simulators around, there are data sets around, there are already there are TNNs, deep neural network pre-trained are around, so you can really use lots of information already to do your study. But for sure there are many other domains, and this is, by the way, one of the challenges that I will highlight later, that ML systems are not only important in autonomous driving, that is not the only critical domain. Therefore we should try to get beyond just autonomous driving, but definitely it's a very widely used domain in this field. So then we should also highlight that there are different types of approaches, of testing approaches, that cannot be distinguished only based on the level of testing. We have seen this and some statistics, but also with respect to the access level during ML system testing. And here we can use similar terminology as we use for classical system. We can say there are black box approaches. A black box approach, a black box test has only access to the ML system inputs and outputs. So it's black box in this sense. Data box goes beyond this. In addition, it also has access to the training and testing data set, which is, for instance, also very useful for metamorphic relations. And finally, there are white box approaches. Many of these model approaches are white box approaches, where also internals of the tested machine learning component are available. This includes the ML model itself, so which type of neural network, for instance, is used, its code, its hyperparameters, its training and testing data, and maybe its runtime state. So lots of information is available there. And actually white box approaches and black box approaches are the most dominant one and the most widely used ones. So the rest of this talk will not be in detail about these white box approaches. I will go to the system level, and then discuss offline and online testing approaches. But still, I want to lose a few words about this topic, as it really has become quite prominent recently. So researchers have transferred the notion of code coverage to deep neural networks and framed different node coverage criteria. Here you can see the basic node coverage, neuron coverage criterion. And neuron coverage is about measuring the portion of the neurons that are activated in a neural network. That you see formally defined here. For instance, if we take this very basic neural network that is shown here, and this is actually from a very prominent paper that I will soon come to, we see here one hidden layer. These are these dark gray nodes. Then we see one output node. And for neuron coverage. There is also a threshold defined, and in this case the threshold is 0, so all nodes that have an activation that is above 0 are activated. In this case, these are from the 6 nodes that we can see here. Nodes are the rounded boxes, the circles, and the output box with 0.25. We see that 4 out of these 6 are actually activated, and therefore the neuron coverage in this case is 2/3, so 67%. You will find lots of information online if you want to get more information about neuron coverage. But the interesting thing, and that I want to point out here, is that there is evidence in this paper by Harold Kanada et al. That actually shows that neuron coverage does not strongly and positively correlate with defect detection. So defect detection in this case means that the predicted and the actual values are different. So this means we have a similar result than also an ICSI paper in 2014 found for code coverage, that it does not correlate with effectiveness. So also for neuron coverage, it does not correlate with effectiveness of finding defects. And then there is another aspect, an additional one, namely that neuron coverage, so increasing neuron coverage, does also not correlate with the so-called naturalness. Naturalness is actually a property that characterizes how diverse your data set is, and how much different labels are linked to your data, for instance, when it comes to images. And here also results show that neuron coverage is strongly, and that neuron coverage here is actually negatively correlated, and therefore also the property of naturalness is not guaranteed. And this shows in general that we need something beyond neuron coverage as test adequacy criterion. We do not need many additional studies that all investigate this in the same manner. We have to go beyond that. And we also need research that goes beyond that. And some of this research I want to show now. It's about online and offline testing, with a special focus then on online testing. So online-offline testing is now another level where we can distinguish testing approaches for ML systems. So offline testing is the testing where the model is tested as a standalone component, and online testing means that the component is tested in a loop setting. This also links to the engineering cycle. Offline is this isolated desktop-oriented approach, and online testing is then where the model is deployed and you can test it in a loop setting. Here you see characterization of offline testing. Offline testing is testing of ML models as standalone components, and the data here for testing can on the one hand come from real-world data, or data can also be data from that is generated, for instance, via a simulator. Often this data, it's cheaper to generate that data. The data is more diverse, and it even needs less time. So using simulators in this context has advantages. Yeah. Then online testing, on the other hand, that is testing in the loop, right? This means that the machine learning component is integrated in a system, yeah, and it's tested in an environment. The classical example is you have your machine learning deployment, yeah, your machine learning component deployed in a simulator, yeah, and it controls based on the image that it gets, yeah, it controls the wheel, yeah, to stay on the road, yeah, classical autonomous driving setting, and for sure it reports then its position back, right? A new image is actually taking, and yeah, so on. We have a cycle, and this is exactly what online testing is about. You're in a loop, and this loop is typically a loop where a simulator is involved, because testing in a real setting is very costly and for sure also full of risk. Just think about autonomous driving. Okay, and online and offline testing, yeah, as sketched here, links actually to the other testing approaches that we have seen before: white box testing, data box testing, black box testing, and the other dimensions: input, model, integration, and system testing. We can say shortly, the more you get to the system level and the more black box your testing approach gets, yeah, the more likely it is that it is an online testing approach. So online testing is really the approach that makes sense on the system layer, right? Because it's not that effective to do offline testing on the system level to really find or identify critical issues. Yeah, and it also doesn't make sense to go to white box here. And actually, there is recent work here by Hak, Fitash, and et al., yeah, that actually compares online and offline testing. And I want to give you a clue of this, because I think this is very important work. Yeah. So the authors here compare how well online and offline testing, this part of the study is more about how well online and offline testing are in finding safety critical scenarios, right? How good they are in identifying them. And they do this in a simulation setting, yeah, that you can see here. And the simulation setting for sure needs a domain model, yeah, that actually defines the properties of the data that is used for learning, but also the parameters that you can configure in the simulator, right? This can be road properties, this can be properties of the vehicle, this can be weather properties, or others. Yeah, you can see that here in detail. And this output, yeah, based on image camera, the steering wheel, or the brake and accelerate is controlled, and we can see it here in the closed loop setting. So, but what is online and offline testing exactly about here? On top we see the offline testing scenario. Yeah, in the offline testing scenario, yeah, we get data. This can be real data or simulated data. This data is then used for as test data, yeah, to then actually measure the accuracy of your DNN, and this is, for instance, done with properties like the mean absolute error. Yeah, and on the bottom we see the online setting, yeah, where the DNN is integrated in a loop, right? So an image is taken from the environment. Based on this image, a decision is made, for instance, how the steering angle has to be changed. Yeah, that is again put back into the simulator to update the driving position. An image is taken and the cycle starts again. Yeah, and what is collected here is the traces over time. Yeah, how the car evolves over time. And this is the finding of the study condensed to one slide. Yeah, actually, what the authors do, they compare the online and offline testing via key metrics. For offline testing, they use the mean absolute error, which you see on the horizontal line, on the horizontal axis in the figures, and on the vertical axis you see MDCL, the maximum distance from the center of the lane, which is the metrics for online testing. Then they define thresholds, which is 0.1 for the mean absolute error and 0.7 for MDCL, so for online testing, but that details are not that important. What is important here is that actually first we cannot really see it in detail because the resolution is not that good, but we can see that there are many data points in the second quadrant. This is the one, or it's the fourth one depending on where you start. It's the quadrant where the MDCL is between 0.7 and 1. So it's the one on the left top, and the mean absolute error is below 0.1. Because what does this mean? This means that a safety criticality is identified by online testing but not by offline testing. And if we zoom in, that is done at the bottom. There are just 2 points there, and these are the points in the other quadrant. This is where safety critical scenarios are identified by the offline testing and not by the online testing, right? First, we see that anyway these points are close to the borders, and when these points are investigated deeper, then one sees that the main reason is that the street was too short, that it was also identified as critical because of a higher MDCL value by online testing. But just to make it short, the conclusion of this work based on autonomous driving data from Audacity is that many safety violations are identified by online testing and they could not be identified by offline testing. So offline testing has very limited usefulness to actually identify real life safety critical scenarios. And therefore we need, especially on the system level, we need more work on offline testing. On online testing and not so much on offline testing, which has been investigated a lot in the past. And now I want to give you an overview of work that we currently do in the area of online testing, and then I want to close my talk with an outlook on challenges that I see to be addressed further by the community. Okay, so what we are interested in is online testing of collaborative AI systems, which we call KAIs. And you see here our example that we actually use and that we also implement in a simulator. It's where a robot arm is working in a co-space with a human, and the robot arm learns from the human in a co-working space how to put the bricks in the right box, how this actually works. For that, the robot has also an image recognition unit, And for sure, this is a safety critical scenario, yeah, because you have to avoid that the robot arm hits the human arm with a specific speed and so on. Yes, you want that the distance is kept and that the relative speed they have to each other is below a specific value. Yeah, and that's the actual setting we are investigating. It's also a very current one. Yeah, first it's not autonomous driving, so we try to go beyond that domain, and it's also current in the context of Industry 5.0, which is exactly about integrating human and AI aspects. Okay, here we again see this setting. Yeah, we have the D and N visual perception component, yeah, that actually identifies the environment. Yeah, it identifies objects, as you can see at the bottom right, and this information is actually fed into the controller. Yeah, that actually actuates the physical elements in the environment. So we have a similar closed loop, yeah, as we have in the autonomous driving scenarios, but just with different actors. And there are several issues that we now have to address. Yeah. So one important aspect is, yeah, that this is a safety critical scenario that is even mentioned in standards. So we have the standards require risk assessment here, but they do not say how to deal with ML components. So one important aspect we are dealing with is how to actually do the risk assessment with ML components, to extend existing standards in this field like DEN 218 to consider this. Yeah, this is one contribution. Then we want to deal with semantically meaningful assurance cases. Yeah, and here adversarial perturbation and neuron coverage are not enough to generate meaningful execution scenarios. We will come there in a second how we deal with this, and we have to understand hazards. Yeah, so hazardous circumstances such as unsafe situations that result in ML component from an ML component must be understood. And in our setting, we follow a risk-driven process. Yeah? This means we do not we really start from modeled risks. Yeah? That is our starting point. And this modeled risk, as you can see here, can really come from application use cases or even from industrial standards. Yeah? So one concrete risk that we already discussed and identified is the one that the robot arm and the human arm needs a specific distance such that the robot arm cannot hit the human arm, right? That's the one. Then after identifying these risks, which are somehow also semantical meaningful hazards, we actually want to quantify how high the risk is. Yeah? So we transform these risks into search-based scenarios within a simulator. Yeah? We will come to that in a second. Yeah? And we use that information that we get from the search-based simulation to actually quantify, and then reduce the risk by where we do not actually do the risk reduction ourselves, because this is then more an organizational domain aspect, how to deal with such elements. Okay, and the first and foremost important thing is now to bring completely informal risks that come from use cases or standard into a semi-formal language that we can then use, that defines parameters in the next step to the exploration of the search space. Yeah? And for that, we adapted the risk ML approach. Yeah? and you can see here basic risk ML model for our setting. Yeah? It has goals on the top, right? For instance, that trust has to be built, human needs have to be respected. Yeah? So such goals can be very high level. And then we refine the goals to more concrete ones like contact doesn't happen or accurate learning of the robot takes place. Yeah? Then we come to the red parts, which are actual risk events, yeah, that harm the formulated goals, like insufficient distance and poor AI quality. And linked to these properties, we always have conditions, right, to these events. Here, for insufficient distance, human-robot distance is below a specific threshold, and ML model accuracy is also below a specific value. Yeah? And at the bottom, we define then the situation, yeah, from which such a risk event might emerge. Yeah? And this close interaction scenario has many variables involved. Yeah? Variables that one uses to define the setting and one that are controlled, like in which phase you are, in the production phase, in the contact area, yeah, or you control the speed of the human, the speed of the robot, and so on. Yeah, and for the online training, yeah, you can have a similar setting. So this is the underlying meta model, yeah, of RiskML. So we have not invented RiskML, but we have extended it by so-called domain features. Yeah. Domain features enrich RiskML by capturing relevant and quantifiable characteristics of the environment that affect the behavior of the ML component, and they are in particular also important in our search space. Then we actually do refine the problem as a search problem, right? So we have our parameter space, which includes the position of the human, of the robot arm. It can include properties like the luminance, so how dark it is, yeah, which influences how well the camera and the image recognition can work. And you can also consider the property, the speed of the conveyor belt, and so on, right? And then we start the simulation, yeah, and actually measure the distance and use this as a fitness function to drive the search, and then to stop at some point and find out whether, yeah, we came to a critical scenario or not. We do this for sure many times, yeah, and doing this many times allows us then also to do a risk quantification. So you see here how we do this. Yeah, so we actually have our scenarios, and for each scenario we finally can decide whether it's compliant, yeah, so whether it's not risky or whether it's actually risky because one of these conditions, like the distance, is actually we go below the distance between the human and the robot arm. And here you just see the quantification depending on the properties of the environment. Yeah, we see the luminance, and we see other values like the RGB or the operator position, and so on, right? And we see at least two critical leaves in this tree. Namely, one is when the illuminance is low, so below 100 lux, yeah, because then non-compliant is already reasonably high, yeah. And another one is when the position of the human has a specific y coordinate, illuminance is higher, yeah, and the R value is above 220, and then we have a non-compliance of 63%, which is also a critical scenario. So we can then also derive from this decision tree, which helps us to actually define what critical scenarios are. We can then also develop rules when scenarios are critical, and these rules define the high risks, and this information can then go back to the risk manager, and he could then make a decision what to do to avoid that the luminance goes below 100 lux, for instance, right? Okay, that's the current state. So this is ongoing work. We soon want to publish a first paper here where we show the results of the search approach. The approach as a whole we have already published in IEEE Computer, and you see the reference on the last page. But from what I have talked now, I finally want to conclude with some challenges. So the first one, and this is then maybe some fruit for further discussion, is domain diversity. This means we need work not only in the area of autonomous driving, but also in other areas like manufacturing, health. They also require solutions, and the approaches are, especially when it comes to the system level, are very often context specific. Then another important aspect, when you especially consider the work that we do, we have to consider the human in the loop. So we also need simulation of human behavior. As these collaborative AI settings become more and more important, we need also to apply and expand human behavior simulations that are around. And on this slide you can see an example, but there is still more and more work needed here. Then another important aspect is also to, let's say, define what hazards are, and to identify what risks are. We need a linkage between some kind of requirements artifacts, may it be standards, may it be use cases, and risks, to then go further with search-based exploration, for instance. And we do this step automated with our risk ML models, but I think there is also potential for natural language processing to further automate that process. Then we need approaches that go beyond just investigating accuracy. We need approaches that also investigate other trustworthiness properties of AI. Safety, we have seen examples here, but also robustness and fairness needs to be addressed, at least with testing approaches. And besides AI system quality properties, we also need to take the test quality into account. Testing, I think, is a very promising area to contribute also to explainable and interpretable AI, right? This is a hot topic, and I think testing can contribute here. We see examples here like our decision trees, I would say. They via a testing-based approach, it helps to make the AI a bit more interpretable. Other approaches are heat maps, that actually use colors to capture the extent to which different features contribute to the misclassification of the input. That's another approach. Then we also need new oracles. Automation is in general key here. And when we also think about, for instance, this human in the loop user interaction scenarios, then we can also learn metamorphic relations from user interaction, for instance via active learning. We could even use virtual reality, augmented reality, to involve humans and to then extend that via active learning. For sure, we also need new and further methodologies for stochastic oracles in this context. Then it's also essential to investigate ML approaches that are not only stateless deep learning networks, as the work that is mostly done on the neuron coverage applies on. So one important aspect is to also test reinforcement learning driven systems, and our system is such a reinforcement learning driven system. There are first approaches around that try to identify mutation of the reward function in reinforcement learning of states and of agents, but this is really very preliminary and there is much more work to do. Then scalability and cost is a big issue, namely when we do this online testing in simulated environments, then we need the environment. So for instance, cloud-based infrastructure where the simulation is actually done. We need the right level of fidelity for simulators. That's also important. Sometimes we do not need high fidelity simulators. This is just expensive. This is time consuming. We need the right level, and we have to balance the effectiveness that the simulators help us to find out what we need and the computational cost of testing. And finally, we also need empirical studies. We need more studies to compare white and black box testing approaches, to investigate the value of adequacy criterion like the one on neuron coverage that I have presented, or comparing on and offline testing. Then we need comparison of different types of oracles, then also an assessment of computational cost and scalability approaches, and the evaluation of approaches in different contexts is highlighted, and also benchmark data and tools should be provisioned to support and enable generalization. Okay, then on this slide you see the references that I have been using and citing throughout this presentation. Finally, here you find my contact data, and now I look forward to interesting discussions. Many thanks for your attention.